Hello everyone. In this video, I will be discussing Learning Objective 2 of Week 10, Interpreting Multiple Regression. So by this time, you know that multiple regression is a dependence technique. So multiple regression is used when you have multiple variable and at least one variable is dependent. Again, I said multiple regression is used when you have multiple variables and at least one variable is dependent. Another condition is the dependent variable has to be metric variable. Metric variable means it has to be either interval or ratio scale. However, independent variable can be metric or non-metric. And in multiple regression analysis, the idea is we have one dependent variable and number of independent variable, and we will explain the variation in dependent variable using these independent variables. For example, the example that I gave in last lecture also, that you are measuring employee satisfaction and you have different independent variables like salary level, training opportunities, development opportunities, and so on. So when you run a multiple regression, you will actually be finding out how much of the employee satisfaction is contributed by salary level, development opportunities, or training opportunities, or leave facilities, so on, or how much variation of employee satisfaction is accounted by each of these variables. One relevant topic we should learn here is dummy variables. As I already said, that multiple regression is used when you have one dependent variable and multiple independent variables, and your independent variables can be metric or non-metric. So metric means interval or ratio, and non-metric means nominal or ordinal. Now, when you have non-metric variable, I mean nominal or ordinal, it might be possible that you use a dummy variable. So what a dummy variable is? Dummy variable is actually an independent variable that we will be using in a multiple regression, where we create these variables just putting 1, 0, 1, 0. 1 will represent presence of a situation or a scenario, and 0 will represent absence of a situation or scenario. Okay, so you, by including a dummy variable, you will basically control the effect of presence or absence of a factor. Let me give you an example. Like in finance research, typically we try to find out what determines stock return. Like if you are calculating variation in stock returns accounted by different variables, we use one dummy variable that represents economic condition. Now, you know that stock price depend on maybe 100 of factors. Now, economic condition, overall economic condition has an impact on the stock return. Like if your economic condition is good, your stock market return is likely to be higher, and if your economic condition is bad, your stock market return is likely to be lower. Now, if you include a variable, just you put 1, 0, 1, 0, 1, 0, where 1 will represent a particular time period where economic condition was good, and 0 will represent an a time period where economic condition was bad, and you include other independent variable and run a regression. If you get that the coefficient of this dummy variable is significant, that will indicate that economic condition or financial condition of a country has important impact or significant impact on stock return. So that's the purpose of using a dummy variable. Now let's take an example. Assume that a toy manufacturer wishes to explain store sales, that is dependent variable, using a sample of stores from Canada and Europe. Now they have three different hypotheses. Hypothesis 1 is competitor sales are related negatively to their sales. Sales are higher in communities with a sales office than when no sales office is present, and grammar school enrollment in a community is related positively to sales. So basically what they're trying to find out, they have a number of stores in different locations. So what determines variation in sales among these stores? The first hypothesis is competitor sales. They're assuming that if their competitor sales increases, their sales decreases. So that's a negative relationship. Sales is higher in community where if there is a sales office present. So it's basically a dummy variable. It will get a value of 1 if it represents a store where a sales office is present in that locality. And it will be 0 when it represents a store where a sales office in that locality is not there. And third of all is grammar school enrollment. They are hypothesizing that if number of grammar school enrollment is higher, that will increase their sales. These points I already discussed. Now they estimated the regression equation and they got this result. So this is the dependent variable and this is intercept. Now this is the coefficient 0.387 is the coefficient for first variable, 115.2 is the coefficient of second variable, and 6.73 is the coefficient of third variable. So 0.387 is the coefficient of first variable, and don't forget our first variable was competitor cells. Okay. If you can remember, we hypothesized that there is a negative relationship between competitor cells and our cells. That means we hypothesize that if competitor cells increases, our cells will decrease. However, we see that the sign of this coefficient is positive. It means that there is no negative relationship, rather there is a positive relationship. What's the coefficient? 0.387. It indicates that 1 unit increase in competitor cells will increase our cells by 0.387 unit. And 115.2 is the coefficient for variable 2, that's the presence of a sales office or absence of a sales office. And you see that coefficient is 115. It indicates that if a sales office is present in a locality, a store in that locality has a sales which is 115 units higher compared to a store where sales office is not present. And last of all, 6.73 is the coefficient for variable 3, which is school enrollment. So if 1 unit increase in school enrollment will increase their sales by 6.73 units. So you can see that all the coefficients have positive signs, so all are positively correlated with the cells. And this is R square 0.845. If you can remember, we discussed R square in the last lecture, and we said that R square represents the proportion of variation in the dependent variable explained by the independent variable. So 0.847, so it's basically 84.5%. It means that 84.5% of the variation in these store cells are accounted by these 3 variables: competitor cells, presence of sales office, and number of school enrollment. So remaining 15% variation comes from different other variables that we haven't included them in our model. And F value is 14.6, where the P value is less than 0.05, so indicates that our overall model is significant. That means that our overall model has substantially explained the variation of the dependent variable. So R square, as I already indicated, and partial correlation indicates that the correlation between 2 variables keeping or considering other variables unchanged. And when we say partial correlation, we actually assumed that this is the correlation between these 2 variables. However, there are presence of other variables as well. Now this is another example. Now look, we have estimated the regression. F statistic is 13.5 and P value is less than 0. So the model is, less than significance level. So the model is significant. And we have 4 variables: sales, lever, experience, and performance. So that's basically the factor that contributes to a sales performance of an employee. And if you can see that there's a positive coefficient of the sales, lever and experience have negative coefficient, and performance also have a negative coefficient. And these are the T statistic. These are the P value, so we can see that sales is a significant variable because its P value is less than a significance level. However, other variables are not. Now, sometimes when we estimate a regression, we may have an econometric problem that we call multicollinearity. Actually, when we run a multiple regression, what do we want to do? We want to explain a variation of dependent variable using some independent variables. Now, if we have, let's say, two independent variables, x and y, now x will contribute to some variation of the dependent variable and y will contribute to some variation in dependent variable. One of the assumptions of regression analysis is these x and y are not correlated. That means the portion of variation explained by x is not related to portion of variation explained by y. However, sometimes it might be possible that we have two independent variables, but these two variables are correlated. So if they're correlated, what happens is you have one dependent variable and two independent variable x and y. Now, x explains a portion of variation in y. Sorry, x explains a portion of variation in the dependent variable. Y also explains a portion of variation in the dependent variable. Now the portion of variation in the dependent variable explained, there will be a common portion that is explained by both x and y because they are correlated. In such circumstance, the regression results become unreliable. So if I summarize, if we have independent variables and these independent variables are correlated to each other, then regression result becomes unreliable. Now, whether these variables are correlated or not, we can check it by a statistic. We call it VIF, variance inflation factor. A rule of thumb is if this variance inflation factor is higher than 10, then there is a problem that variables are correlated, and this problem is called multicollinearity. For example, in this case, you can see cells and liver, they have, both of them have VIF 56 and 55, so they are way higher than 10. So actually multicollinearity problem exists here. So the simplest way we can solve this multicollinearity is to exclude one of the variables that are correlated. Okay, there are some other ways we can solve this multicollinearity problem. However, I don't think that they are the scope of this course to discuss. F-test, as I already said, that when we run a regression, we get an F-statistic and a corresponding p-value. So F-statistic basically tells you that whether a substantial variation of the dependent variable have been explained by the independent variable. That means that if the overall model is significant or not. If the p-value corresponding F-statistic is less than the significance level, it indicates that the model is significant. That means a significant portion of the variation has been explained. So this is how we calculate F-statistic. However, we don't need to calculate them using this equation because when we run multivariate regression in Excel, it will automatically generate F-statistic and a corresponding p-value. Now this is another result of multiple regression. So when we have a multiple regression, the result, the first value or the first statistic that we should look at is R squared. Okay, for example, here you can see R squared is 0.7. As I already said, that R squared will indicate the portion of variation in the dependent variable explained by the independent variables. For example, in this case, it indicates that 70% variation of the dependent variable is explained by the independent variables here. The second statistic we should look at is the F-statistic and its corresponding p-value. So you can see here F-statistic is 19.38 and p-value is less than 0.05. So the overall model is significant. Again, what's the meaning of overall model significance? Overall model is significant means our model has been able to substantially explain the dependent variable. Okay, so next values we should look at the coefficient of the variables. For example, here we have three variables: hours, budget, and state. We have coefficients 0.99, 6.6, minus 66. So first of all, you should look at the sign of the coefficient. Is it positive or negative? For example, hours and budget, they have a positive coefficient. It means that they are positively correlated, or they have a positive influence over the dependent variable. That means if hours and budget increases, dependent variable will increase correspondingly. However, the state has a negative coefficient. It indicates that with the increase in this variable, the dependent variable will change in opposite direction. That's the direction of relationship. Now, strength of relationship will be indicated by their corresponding p-value. For example, if you look at the p-values for hours, budget, and state, you can see that only hours p-value is less than the significance level. That's 0.05. So it's 0.0015. So it's less than 0.05. It means that among these three variables, only hours has a significant impact on the dependent variable. And if you look at VIF, it's 1.96, 1.89, and 1.65. So they are less than 10. So these variables are not correlated. That means there is no multicollinearity problem. Unfortunately, we will be using Excel for running the regression, but Excel does not provide VIF result. So at this stage, I am not expecting that it will check multicollinearity or the corrective data for multicollinearity. I just wanted to let you know the concept. That's enough for this course. That's the end of our discussion on Learning Objective 2. Please watch the next video for our discussion on Learning Objective 3. Thank you.